Ladies and gentlemen, today we're going to break down the insertion sort algorithm that we wrote in the previous video. As you can see here, I've got the algorithm written out along with some line numbers. And we're going to take a look at each of these lines or statements, and we're going to determine two things: how much time it takes to run the statement and how many times the statement is going to run. I've written down two columns for us to analyze that for each statement. We know that computers have a brain, the CPU. These CPUs execute instructions, but computers vary bigly, and the execution time of instructions also varies. So, in order to analyze these algorithms, we need to do something. Let's take a moment and imagine with our magnificent walnut a computer that can execute basic instructions like assignment, addition, subtraction, and so forth in a constant amount of time. One execution runs immediately after another. Now that we have our imaginary computer, let's throw our code into it. We are going to take and view this entire line by itself because there's nothing really that complicated going on. I is equal to 1, that's assignment, we've got a comparison, and we have an addition. Nothing complicated is going on, so we can assume it takes a constant amount of time to do this. So we're going to treat it as one statement. So let's look at this first line. How many times is it going to run? Well, it is going to execute once for each item of the array. So we're going to set this equal to n. And like I just said, it takes some constant time to run, so we're just going to call that C1. The second and third lines take a constant amount of time as well, and we're just going to call these C2 and C3. And they are each going to run n minus 1 times. So lines 4, 5, and 6 is really where our britches start to sweat a little bit. And if we look at each of these statements, they're simple statements, so we can say that they run in a constant amount of time. So we can say C4, C5, and C6. But determining the number of times that they're going to run is a little bit of a pickle. If we took a look at this first line of our while loop, it is going to be executed once for every time that we need to swap an element, plus one that involves the initial check. So that means for every index I, that is going to run ti times. So this is for a particular index I. But in reality, if we want to get the total number of times it's going to run throughout the entire algorithm for every index I, this actually turns into a sum, where I is equal to 1, that's our beginning, we go to n. Okay, that is our sum, that is how we describe this. C5 and C6 is, well, the same. And you can look at that and you say, ew, that's gross. You'd be right. But we still don't have a runtime. We've just got a function that kind of describes it. So let's consider an input real quick. Let's consider that we have our worst case input. Let's say WCI, which is, in terms of insertion sort, our worst case input would be a reverse sorted array. So that'd be something like 5, 4, 3, and 2. So for each index I of our array, we're going to have to execute lines 5 and 6 I times. So the total time works out to be, in this case, 0 plus 1 plus 2 and plus 3. And if our array is bigger, it goes all the way to n. And if this looks familiar to you from discrete mathematics, you recognize this as a simple sum that we know the answer to. How many times is it going to run total? And that is equal to n times n minus 1 over 2. And in the case of these two sums here, because they run one less time, this actually ends up being, if you remember from discrete math, once again, equal to that. So those go here, this guy goes here. So I'm going to rewrite our time to run in the number of times once again, and then we will finally be able to solve the total amount of time that it takes to run insertion sort. I totally forgot to mention our little friend over here, line 7. He is going to take a constant amount of time as well. It's just an assignment statement. And he is going to run n minus 1 times. Easy. Alright, on to the finished stuff. So in the case of our worst case input, this is what it looks like. And so in order to get the exact running time, we just need to combine this. So the time to run is C1 times n plus C2 times n minus 1 plus C3 times n minus 1 plus C4 and so on and so forth. I'll continue this. So as you can see here, I ran out of room and had to wrap around to the next line, but this is the total time of our function, and damn is it ugly. And if you think that sucks, I can't do that for every single algorithm, well, you're in luck, because we actually don't care about most of this function here. The reality is, when we are considering algorithms, what we are concerned about really is what is called the order of growth. And what is the order of growth? Really, that is just the leading term of our function. So in this case, what is this going to be? If we break down these summations here a little bit, it ends up being something like n squared minus n over 2. Okay, we have a lot of those happening. So if we look at the entirety of our function, all we have is n minus 1, n minus 1, n minus 1, and then we have these different n squareds here. And so in reality, the order of growth of our function is actually n squared. And while we are on the topic of ignoring most of this stuff, we can actually ignore the constant coefficients as well. Because honestly, we are concerned with as our inputs become astronomically large. And this is what we're going to cover in the next video, which is asymptotic analysis. So we're concerned with this as n tends towards infinity. That is an ugly infinity symbol, but you get my drift. And so these smaller coefficients and smaller terms end up being completely irrelevant. And what we're concerned with is really this leading term. So you can say that you found the exact running time of insertion sort here in the worst case. And for kicks and giggles, let's do insertion sort in the best case. So let's consider the best case. And the best case for insertion sort is when our array is already sorted. So say we've got 4, 5, 6, and 7. For each index I of our array, we do not need to enter into this while loop at all. So we execute this outer while loop n minus 1 times because we still need to do the comparison. But C5 and C6 aren't executed at all. C7 is the same, n minus 1. And so you can add this up, C1 times n plus ... all that other stuff. And like I said, we ignore the leading coefficients and all of these smaller order terms, and we are only concerned with the order of growth. And so the biggest term that we run into here is n. So that is what the running time of insertion sort is going to be in the best case. And if you want to talk average case, well, we can do some more summations and stuff like that, but I don't really want to. You are free to do it on your own, but just know that it ends up being the same as in the worst case. All right, well, that is it for this video. In the next video, we are going to learn about big O analysis, asymptotic analysis, and how to do it properly. Thank you so much for watching. Let's go rest our little walnuts and come back for the next one. If you liked it, please like and subscribe and have a great day.